Okay, so welcome to the ComputerNet School Physical Computing Community. My name is Pete Dring. I'm Head of Computing at Fulford. We will definitely finish by 5 o'clock, but I understand that life is busy, so that if you need to disappear off to deal with students or pets or anything else, then that's absolutely fine. So I'll talk through what's going to happen. We've had a question about, do we have any project ideas? I've got a couple of things that you can vote for that we can go through. So do feel free to, I'll give you a primer of these so you can be thinking through. We probably won't have time to go through all of these. So if you're joining, welcome. That's great. If you're happy to mute your microphone, we've just started, so welcome. So these are the project ideas that we'll go through today. By no means exhaustive, but how to get started with just basic animations and images. We've got a football match apparently this evening. So every time I see one of these substitution boards, I think, oh, it's just a giant micro bit with big buttons on the side. So we could try and make one of those. There's a compass using some of the sensors. I've got all sorts of gadgets just about to fall off my desk. I try and dissuade teachers from booking my room by leaving my desk as messy as possible, but it never seems to work. But you can see some of that, and we can talk through some of the hazards of that. And I thought maybe again with a football theme, we could make the microbit sing the national anthem if we can kind of tilt it to get the pitch right. We won't have time for all of those, but you can vote in the text chat which ones you want to do. For me personally, I think the pedagogy is more important than the projects. So some of you might have questions about, how do we store them? How do we get the stuff out? How do we manage all of the behavior within a class when you're sending stuff out to students? How do you raise money for it? Are there any ways to get them for free? What IDE do you use? People always ask that question. What happens when you have a sea of hands when people don't get things and when things go wrong? And then how do you differentiate? There are some students that go really fast and some students that go really slow, and we want all of them to leave feeling like they've achieved something. How on earth do we manage to do that? So I haven't got all the answers, but that's what we want to try and touch upon. And if we don't get through what you want me to get through today, then my email is on here. Do get in touch or join the ComputerNet School forum and continue the conversation at that point. Okay, so far we've established that the official word for a bread roll is a bap in Yorkshire. Not been too much argument on that, which is unusual. I put this on here because loads of people like to talk about what they can do with physical computing, but for me in a classroom, there's three questions. It's not just what can you do. The more important questions are why and how. So when we train as a teacher, we're told that we have to give specific learning objectives. I've had a brilliant trainee recently who's very good at explaining what students should do and then got better at modeling how students should do it. And it's this question that he really thrived at and excelled at towards the end of his training. That's the one that I think really matters. So this is the display board that I put on every classroom in my school and in all the corridors. The bigger picture here is not that students can have fun with some electronics, although that is fun. It's not just that students can have a creative time, although I think coding can be one of the most creative things that students do in school. It's because I want them to leave school empowered to change the world. And I think sometimes physical computing and coding is a really empowering way of doing that. So that big why question, rather than just we're going to write some code to display a smiley face, it's, well, how can we come up with an idea to make a new medical device that could actually support elderly people with loneliness? It's putting the ideas in context that I think makes the biggest difference for boys and girls, but girls particularly. All right, so this is your first opportunity to vote. Just put a letter or a number in the text chat, and then depending on how I'm feeling, I'll ignore it and just go for what I want to do. But it is an opportunity for you to choose. Apologies as well. I went for a run over the weekend, which doesn't happen very often, and I scratched my glasses. So all I can see are smears. I'm telling myself it's that rather than just old age. Okay, so we've got 3 and 5 so far. So let's start with IDEs and then differentiation. As we look at IDEs, it'd be great to have a look at one of A, B, C, D, or E. So if somebody can choose one of those, that would be fab, please. C, great, okay, accelerometer and magnetometer. Yeah, we're going to start with the excellent microbit Python editor, microbit classroom. In fact, we'll just start with the microbit Python editor. And I really like this. It's taken a lot of development to get to a point where there's all sorts of handy guides to get started. So we've got a simulator on the right hand side. So if you can put into the text chat a yes or a no. Yes means you've got a microbit in front of you that you can play around with. No means you haven't got one in front of you. That'd be really helpful for me, please. Bring the text chat back up so I can see what you're saying. Yeah, okay, so most people haven't got one. So we're going to rely on the simulator. The simulator is essential, especially in a classroom, because actually a lot of the physical computing that we do is so much more valuable when they can tangibly touch it, but it's a lot more hassle getting it out to students every single lesson. So a lot of the work can be done on a simulator, and it just reduces cost and complexity and improves behavior, as long as it's not just purely relying on the simulator. Okay, so hopefully you can see this code here. We wanted to make a gyroscope, I think. You voted for a compass. So in order to do that, we have to have something that can point. So let's start just with a pointer that can point in different directions. We've got from microbit import everything. Normally in Python, you'll have import and then the name of a module. Which you can still do on a microbit, but you end up having to write microbit dot every single time, and it's a bit irritating. So we're going to have microbit dot display dot show image dot, and then there's all sorts of different images that we can use, and we want the clock ones. Are there some ones that we can run with here? Oh, and of course it doesn't recognize what image is because I forgot to do the microbit dot image dot, and then what is the clock here? We've got all the different clock ones or clock one. We'll start with that and simulate it. Okay, so you can see it's like a clock that's pointing to 1 o'clock. Is it clock 12 that will go to the top? There we go. All right. Now, the one thing that I wish that we had in the Python microbit editor is a save button that would save to a link that we can quickly share. And I don't think we've got that at the moment, although we've got someone from ARM who might correct me. So apologies if I've got that wrong. But one thing that the Microbit Foundation have worked on that I think is brilliant is a way for you to share your code really quickly with other students. So we're going to try that out now. Let's see, it's the Python microbit classroom. Apologies about the noise of me typing in the background. Just proves I'm not like lip syncing. I'm trying to carry on as we go. Right, let's have a new session today and let's call it Compass. Oops. Let's start with Python. You can code in all sorts of other languages, but the focus of today is all about Python. I introduce physical computing for year 9, deliberately not introducing too many different languages. I want to try and keep it as simple as possible for when students are learning to code. They do some block-based languages, and there's a transition into text-based, but the only text-based language we show them is Python. Otherwise, they just get overwhelmed with doing the same thing in so many different languages. There's advantages of doing it that way, but it's not something I've chosen to do. Right, that code here is not the same as the one I've got here. That's the code that I want to give to you. So let's plot the code that we want to share with students. Back to setup. Here we go, and start a session. All right, if all is going well now, I should be able to invite you by typing this into the text chat. If you can click on that link for me, please. And now the name that you put in will appear in the video recording. So if you're happy for me to refer to you by name in the video, put your actual name. If not, you can make up a cartoon character or something like that. Fab. Thank you, Baron. Thank you, Shefali. That's great. All right, so hopefully you'll see what students see when they join your class. They've got access to some code, and you should be able to run it. And even though you don't have a physical microbit in front of you, you can see what that microbit does. And it's not very exciting yet. So let's have a look. I'm going to edit the code. I know that you'll have your code and the Teams sharing screen. I'd recommend that you watch the Teams sharing screen. Depending on what device you're on, it's going to be difficult to code along at the same time. So don't worry, just maximize my screen and I'll share the code with you at the end. Okay, let's refactor it. Let's change it to from microbit import everything, which usually is considered bad practice because it's called polluting the global namespace. How geeky does that sound? But for us, it's really useful. It's saying everything in the microbit module we don't need to refer to explicitly anymore. We can just assume that it knows we're talking about a microbit. There we go. From microbit import everything. So if we've got 12 o'clock and then 1 o'clock and then 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, 7 o'clock, 8 o'clock, 9 o'clock, 10 o'clock, 11 o'clock. Here we go. Let's see. So I'm pressing home and end on the keyboard to try and get to the beginning and the end. Here we go. Now, when I run this, I'd like you to type into the text chat what you predict is going to happen. I've probably forgotten one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. What's going to happen when we press run? So if you're aware of PRIM, Dr. Sue Sentence's pedagogical approach, she encourages people to predict what's going to happen first. So thank you, Shifali. We've got a prediction that says microbit will show these numbers as images. Let's have a look and see. So all we can see is an 11 o'clock at the end. So lots of potential misconceptions here. So a lot of students will think that it will show them one after the other. A lot of students will think that it will light up and then 1 o'clock, 2 o'clock, 3 o'clock, and it will leave them lit up. So it ends up all being lit up. So everything that you've written in the text chat is logical. But the reason why we can only see 11 o'clock, Lorne, excellent, well done. It looks like it's happened simultaneously. The microbit runs, I can't remember the exact clock speed, but it's a lot faster than my brain. So it will display 12 o'clock and then it will display 1 o'clock, but it will go so quickly that it just doesn't register for us. So we could slow it down. We could put a number of milliseconds in here. Let's have 0.1 of a second and put them in. So it should slowly go through these ones and then instantly jump to 11. Let's have a look and see. There we go. So is there a better way of doing this? Well, yes, there is. We could make a list of all of the clock images, but actually that's already done for us. There was image.allClocks in here. If we print that, and you can print stuff, I mean, you'd only see it on this read, evaluate, print loop, the serial in here. There's lots of images in here that perhaps we haven't understood yet. We're going to come back to that if anybody chooses option A in a moment. So let's have a look. Where did we get to? We've got all of these images here. Let's get rid of everything except for these 2 lines and say, in fact, let's just display the very first value of all clocks, or the second value of all clocks, or the third value, etc. And at this point, hopefully we should be able to iterate round that list to go through each value. Let's see, for I in range 12, because there's 12 different ones, and we're using I as an index, as in, like we've got the index of a book, the page number of the book, we've got the index of an array here. I'm just going to replace that number with I, so that it will display the first one, the second one, the third one, the fourth one. And we've got the same problem we had before. It's shown them all, but ended up with this last one here. Let's slow it down to 1/10 of a second on each one. And that's great. Okay, at this point, I want to show you how we can get the code from the screen onto the actual microbit. So I'm going to save this. In fact, How do I send it out to you? Let's send the code to all students, and then hopefully, can I do that? Yeah, there we go. You should have a choice now of whether you want to keep your code or whether you want to get my code. Rather irritatingly, if you choose my code, it deletes everything you've done, which is a bit of a pain for creativity. So you might be worth verbally saying to your students, right, I'm going to send some code for you. If you've got anything you want to keep, copy and paste it into your workbook, into your whatever you use for keeping track of student work. We can work from there. Okay, how is this going to work? Let's open up a webcam. And on my desk, I've got a microbit. This is a version 2 microbit. You can tell because it's got the little lumpy bits down there. I've got some version 1s as well. The main difference is that the version 2s have a little speaker in, which is actually really irritating because they're just really beepy in the lessons. So I tend to use just the version 1s because we've got more of them. There's a lot more memory on these. There is a limit to how long your Python program can be in terms of lines of code on a version 1. And there's some extra stuff as well on a version 2, like this thing is a button that you can press on version 2. And it's just a design that doesn't do anything on a version 1. But otherwise, they're the same. There's probably a bit of a price difference. I'm not entirely sure. Right, so it's just plugged into a USB port. There is a center microbit option, which in theory should connect to web USB, but it's never worked for me in my school. You should be able to do it once, but I always get this error, and I don't know how to fix it. So I'm going to do it a slightly different way. Right, so if we press save, we can give it a name. I'm going to confirm it, and it should now download a hex file. Now, what students will do is they'll click on that hex file, and it'll open in Notepad, and they'll say, well, nothing's working. At GCSE, we talk about hexadecimal, but I think it's worth flagging up to Key Stage 3 that this is just a representation of your Python program, a couple of lines at the bottom, but actually the whole of the Python programming language, the runtime for how to interpret everything. Now, students don't need to understand or remember any of that. All they need to do is save it to generate that hex file. And then they find that hex file. And when their microbit is connected, they'll see it like a USB drive, drag it across. And you call programming an embedded device flashing. And I like that for a microbit, if I can get back to the camera, it is actually physically flashing, which is nice. It can take a few seconds, but when it's done, hopefully, we should see that little clock face going around. I'm going to push the button on the back, the reset button, which should run the code again. And there we go. All right, so you said we wanted to do a compass rather than just a spinny thing. We want it to point in magnetic north. So rather than just spinning round, we want to get a sensor value. And you also said you wanted to explore different IDEs, but maybe we'll come to that next session. Let's try and keep it as simple as possible. Right, reference. It's not accelerometer, it will be compass. And where is that? Here we go. Now, I really like that we have some code that you can just drag and drop in here. So if we pop that here, we should be able to get the compass coordinate and do something with that. So let's see. Compass.getX. We want to know what the total value is. So for this, I'm going to go to a different IDE. One that we'll come back to. This is the national anthem a little bit later, and we'll do the same from microbit import star. It's not as pretty, it's not as easy to use, but the link to the help and tips, I know there's something for a compass that we can use here. Let's have a look. Compass, where are we? Let's see, Control F, compass, there we go. Is there an example? Yeah, here we go. From microbit, import everything. Now we've got some stuff that we recognize and some stuff that we don't. The calibrate actually gets your microbit to play a little game because you've got to work out which direction it's pointing in first, but once that's done, it's not needed. So I'm going to get rid of that. The while true repeats forever. We could actually use that while true in the program we had so that the clock goes around forever. While true, and then indentation, select them all, press tab to the button to the left of Q, which means this is going to go on forever and ever and ever. Now, students get confused about what while true means. We could put anything in here, whilst it's raining, whilst it's Tuesday, whilst I'm happy, whilst I'm hungry, but true is always true, which means this is going to happen forever. It's like a forever loop in Scratch. So hopefully, if we run that, time goes on and on and on forever, like listening to me in this session. The while loop we're going to do here, we've got some maths saying, well, work out which direction the compass is heading. We will do integer division by 30 to split it up. Instead of just, 360 degrees, we'll divide that by 30, so we've got 12 different headings. Do 15 minus that so it can be in the middle, and then ignore the actual result of the division. We just want the remainder left afterwards. So the maths is probably beyond most Key Stage 3 students, and certainly beyond me at the end of a long day. But hopefully we should be able to see if we change the direction that the compass is heading, it should spin round. All right, so I'm going to share this, Control S. This is the feature that I think is missing, the only feature that I think is missing from the Python editor, the ability to save it quickly and get a link. So I'm just going to put that into the text chat so that you can try it out. You can press run or Control and enter. If you have got a microbit at home, the process is similar. We're going to download the hex file, and then we're going to copy that to the microbit. Where is it? There it is. Drag it across. Let's have a look at the webcam. It's flashing. You can see it behind here. And then hopefully, when it's finished copying and finished flashing, if I twizzle this round, it should always point towards the north, as in where everybody should live. Don't understand why anybody would live down south. Sorry. Okay, so this is the little game I was talking about to calibrate. You have to tilt it to fill the screen. You can see the text scrolling across. You only have to do this once. And it's so that the sensor can understand which way is up, which way is down. And you can see I'm kind of tilting it until all of those LEDs are filled up. Now, some people look at a microbit and they think that's so basic and pointless because you've only got 25 LEDs. What on earth can you do with just 25 LEDs? And they're right, of course they're right. But actually, the simplicity is the beauty. If you try and write a first-person shooter, it's telling me again, tilt to fill the screen. I'll try and do this without waffling at the same time. If you try and draw a AAA game and write the code for it, it's just impossible. You can't, as an individual, do that. Certainly not in an hour. Whereas you can get some really creative animations here. Come on, fill the screen. You might have to take my word for it when it is tilted. Come on, last little one. There we go. One more to go. No, sorry, two more to go. This last one in the corner. Come on. There we go. It's got a smiley face. And now it's telling me that north is that direction. And if I tilt it round, it should still point in that direction. Now, I don't worryingly know which way north is, but I'm going to trust it. I'm going to say that that is magnetic north. Fab. Okay. All right. Let's go back and vote again. We've talked a little bit about IDEs. We've said create with code does not look nearly as nice as the Python microbit editor. Microbit editor is brilliant for code samples, but doesn't let you share the code. The classroom feature is excellent for sharing the code and monitoring what students do. So that seems like a win from my perspective. All right, I can't see the text chat. Could you type in some other suggestions for me, please? So we've done a little bit on images. That's the shortest one. We've got E and D. And anything on pedagogy? Anything else you want to talk about on these? Yeah, fab. Okay. Right, let's have a look at sending and receiving radio first. and then we'll talk about differentiation at the same time. How can we do this? If I start with looking at the webcam, you'll see next to me, I've got a couple of different devices. This is a Kitronic robotics board where you can plug in some motors and you can plug in all sorts of different devices. The gold on here is there because it doesn't tarnish and because it conducts electricity really nicely. And it's worth talking with students that you can get quite a lot of money if you recycle electronics, because there does tend to be a significant, not huge, but significant amount of gold that you can recover. So these edge connectors are great. They just slide in. And then I've got another of the same devices here, but this time just with crocodile clips. Sorry, I'm going to try and autofocus because that looks horrible. Just some crocodile clips plugged into some motors. And then it's the same code that's actually running on both of these microbits. It's just some Python code that will either send a radio message or receive a radio message, and I'll show you that code in a moment. But if I switch on this one, to begin with, it's got a number on here, and this is like the substitution board that we could do if we've got time. We've got 15 minutes left. You press a number to choose a channel, and this allows us to have multiple buggies running at the same time. So I've chosen channel 4 here, and then you can do manual control, where you can see a wheel going round. Or if I get another microbit, it's just got some batteries on the back. Hopefully, if I switch this on and go for the same channel, that's channel 4, 1, 2, 3, 4, choose that channel. Yeah, hopefully, if I push button A, then the left wheel moves. If I push button B, the right wheel moves. Now, hopefully it's not going to fall off the desk and cause carnage, but these devices were part of, I think it was a kit in a box, which was quite expensive, but if anyone asks about funding, I'll show you how you can get £400 for free to afford, this kit in a box or anything else, as long as you run an event that is free for at least 25 students. Do ask me about that because I'm likely to forget. So how do we do that? How do we send radio messages? And then how do we differentiate it? That's the challenge. Right, let's find an IDE and work from here. Oh, as well, let's share the code before I get distracted. So this looks familiar from microbit import everything. This looks familiar. We're looping forever. This is new. We've got an if statement that says if we're pressing button A, do something. If we're pressing button B, or if we're touching this. Now, bear in mind, this bit is only going to work on a microbit v2 because it's not a button on the version 1. So what we've got to do is import radio and then send or receive. So what does GT left and GT right? Now, I'm not particularly confident that this is going to work, but we'll try anyway, just in case. Now, I don't know if any of you are on the CAS forum. If you are, you'll know Richard Pawson, who's a bit of a hero of mine, and this device is thanks to him. He provided this. This is called a Gigatron. Let's see if I can rearrange the visualizer. And it's just essentially what's inside a microbit. So all of the TTL, the transistor to transistor logic, AND gates, OR gates, and NOT gates. Look, you can see them here. They're just diodes that make up the instruction set, and lots of AND gates, OR gates, NOT gates for a whole gaming computer. Now, this is designed to be run by a keyboard, but instead of a keyboard, what we've got plugged into it on my desk is a microbit pretending to be a keyboard that is then sending the signals to control this gaming computer. So in theory, if we plug this in and switch it on, let's plug it in and then twizzle it. Sorry if you're getting dizzy. This is going to be upside down. Sorry, you're going to be even more dizzy. It's like VR motion sickness. There we go. So that is the gaming computer. That is the result of the gaming computer. There's a little manual controller down here that I'm going to wiggle and hopefully move it so that we can select racer. going to switch it off and back on again because it's a bit temperamental. There we go. We've selected the racer game. Push in. And then the fun bit. This micro bit, if we code it correctly, I want to be able to push a button and it moves the car. Now, although it's plugged in, we're just getting power here. We could power this by a battery. And much more importantly, in a classroom, you could get a whole class full of students. You could have one student that just makes the car move left on their microbit. You could have one student that just makes the car go right. And obviously not everybody has got this retro gaming computer in their room, but you can do this with anything. I've got a cheap radio controlled octopod that shoots a Nerf gun, taken to pieces, just shove a microbit inside. Same principle, listens to a radio signal. If it receives it, it moves, it shoots, keeps students on their toes so that hopefully they don't mess around in the lesson. So how do we do it? Should we test it? Should we see if it works? In theory, if I run this, Control Enter, download the hex code. Let's get that into the microbit. Will it work? Let's see. Have a look at the webcam. So we can see it's flashing at the, sorry, I'll try not to move that. I know that's really dizzy inducing. Right, probably going to have to switch it back off and back on again. Don't know why that's necessary. Choose the racer, push it in. Now, will the car move when we press these buttons? I really hope so. Oh, it does. Now, this is so exciting when you get a group full of year nines coding their microbit that sends a radio signal. And then we can have the important discussion. Well, hang on, we've got 32 students all sending a radio signal and this car is going crazy. So how do we make sure we only get the signal that we want? And then we can talk about encryption, we can talk about different radio channels, we can talk about protocols. The opportunities are endless for this type of thing. How do we get it to move forwards? I should be able to touch it, but it's probably crashed. Let's just move on and pretend that it all worked and hope for the best. All right, so I didn't do this with every class. For radio signals, I got students to begin with just display dot scroll, put some text in here, and I asked them to come up with a powerful motivational quote. So they went off and Googled this, and it kept them busy, or they came up with something like that. The cheesiest one was today's problem. Oops, if I can spell, is tomorrow's opportunity, something like that. Again, spelt it wrong. Sorry, hard to type and talk at the same time. So we started off just having one inspirational quote, and then we had it so that if you press button A, it shows a quote, and then button B, I don't know, it gives an excuse for not handing in your homework or something like that. And then instead of display.scroll, which just scrolls the text across, we can import radio and do radio.on, and we talk about power consumption because students will know that if they turn on Bluetooth and on Wi-Fi on their phone, their battery lasts less time. So we have to actually turn the radio on, otherwise it's going to use a lot of a bit more electricity. Then we can radio.send and send this instead. So this is just running on the simulator. When I press run, it's not going to send that to control and interfere with the games console or the little buggy or anything like that. You have to actually download it and put it on a microbit for it to send. But in a classroom, I would have probably Thonny running in the background. Have I still got that open? Yeah, I have. Here we go. So Thonny is a downloadable program rather than a website. Which just means you can get instant feedback and monitor that REPL, that read, evaluate, print loop. So from microbit, import everything. Turn the radio on. Oops, we haven't imported radio yet. Loop forever, so while true. Let's receive something. Radio.receive, just like radio.send, but the opposite. And we need to store that. We get the return value and we store it somewhere. For now, let's just print what we get and sleep. Now, this sleep is essential. Students will know that sometimes their phones get hot and they seem to crash. And that's because it gets stuck in a while loop. The code just does something repeatedly, and it uses all of the CPU capability and uses all of the battery. In order to prevent that, we just need to sleep a little bit. It still looks like it's working. It just slows it down so it doesn't use all of the CPU process and not all of the battery consumption. All right, let's see if this can connect to the micro bit. Here we go. I'm going to press run. And at the moment, it's, look at that. That's me typing and speaking at the same time. I don't want to print. I want to print the data that we've received. There we go. I've got nothing. That's not great. So how about if we only display what we've got if the data is not equal to none, not equal to nothing. Let's try that. Fab. So it doesn't look like anything's happening. Fine. Let's just do a print listening to begin with, so we can see that something's happening. Great. So this is running in the background. This is what I had running in my Year 9 class earlier today, and I shared code like this for students to work on, and they had to put their name and their inspirational quote. And then we talked about how do we differentiate. So when I share code with students, I always try and put 3 challenges on. One that's easy, something that everyone can do with minimal coding knowledge. Change the quote to a inspiring, to your own inspiring quote. Change it so you can press button A. Okay, so we give them something that they can relate to. We give them something that they can do easily, and it's a little bit more challenging for them to do. When they get this on their microbit, I usually share my screen with students so they can see the message appear on here. And of course, students are going to put a swear word, or of course, students are going to put something that's ambiguous and hard to work out who's got it. But that's, again, another good teaching point, because I can see who's written what code. We can track it down and we can sanction it accordingly. But more importantly, we can talk about the need for encryption. We can talk the need for protocols, for safeguarding duty, for rules, all that kind of stuff. Now, I haven't got a class full of students typing stuff. Even if I share this with you, I'm going to put this in the text chat again, and you run it in the simulator. You're not sat in the same room as me. You haven't got a physical microbit. So when you press run, that is not going to appear on my screen. But I do have, let's see, where are we? Have we still got the camera open? Yeah, here we go. If I put that on one side, sorry, again, making you dizzy. If I point this down here and keep Thonny up on here, sorry, twizzle it round so that you can see it in the right orientation. Let's switch this on. Hopefully, there we go. Can you see that? We've got, when I push button A, you can see it's sending a 2. It's sending a 1 when I push the button and a 0 when I stop pushing the button. And I'm not quite sure what that 1 means. That must be the name of the button, and maybe the 1 would be the channel. Let's try that. So let's choose a different channel this time. Yeah, there we go. All right. How are we doing for time? We're coming up for questions and answers.